Okay, we're going to look at, in this video, gamma radiation, and in particular with gamma radiation, its inverse square proportionality. Now, I hope you can remember from probably work you've done at GCSE that if you had a source of radiation, then this is going to give off it could potentially give off three types of radiation. One of them is an alpha particle, which is 2 protons and 2 neutrons, and that is a helium nucleus, which is the same as alpha. One of them would be a fast-moving electron, which is beta, we'll call it beta negative, or the other one is a very high energy electromagnetic ray, which is gamma radiation. And of course, this is an electromagnetic wave, so therefore it's subject to the inverse square law. And just so I can remind you what the inverse square law is, it suggests that from a source we have radiation that spreads out over an area. And because the area keeps increasing, so the intensity of that radiation will therefore decrease over that area. It's similar with gravity, similar with electromagnetic radiation. And that's for a gamma source. So the gamma rays pass out from this point. Now, before I go into details, it's probably worth getting down some definitions here. Usually we talk about intensity. And with intensity, which is usually given symbol I, that's measured in watts. That's measured in watts per meter squared. So what we're looking at is we're looking at the power per square meter that falls on something. So we have the square meter here. We're dealing with an area, of course, but we're actually talking about the energy falling per second, intensity. So it'd be fair to say that the gamma coming out from this source has an intensity. However, the only way that we're going to work out how much is coming out is by using a Geiger counter. And I'm sure you can remember the look of a Geiger counter, or a GM, Geiger-Müller tube, plus counter. And what happens here is you have a little sensor well, it's not really a sensor, you have this entire thing here is a Geiger-Müller tube. And as the radiation passes through and into the Geiger counter, so it causes ionizations to take place inside. If ionization does take place, then you have a cascade of ions between one side of this material and the other side, and the inside sensor and the outside, and that conducts electricity and causes a pulse, which then goes to the counter and is registered. So we need to be careful here about our definition of intensity versus the number of counts. It might be that only 1 in 5 gamma ray coming in results in an ionization that causes a pulse to occur. So therefore we can't directly say that the intensity is the same as the number of counts. However, what we can say is that they're going to be directly proportional. So we could say the intensity is proportional to the count rate. And of course that might be per minute, it might be per second, etc., etc. So when we deal with electromagnetic radiation experiments, we will be looking at a Geiger counter and then saying the count rate will be directly proportional to the intensity. So therefore we'll be able to work out if I've got so many counts in this position here, if I were to move out further, I would get fewer counts because I knew my intensity would be dropping in accordance with the inverse square law. Just to expand on the inverse square law a little bit more, we can say that the intensity is equal to the original intensity divided by the area in which the radiation is spreading out over. So here's a small part of the area. We're interested in every bit of this sphere that the radiation might be emitting from. Good. So with that in mind, let's have a think of how, one, we can measure and we can validate this inverse square law, with a Geiger counter, and two, some problems and how we're going to deal with those. Right. Let's deal with experimentally now. Experimental proof. Good. Let me place my source in again. I draw it like this because this is pretty much how it looks if you've seen it in the classroom. This part here is to hold the radiation, and this part's where the radiation is coming out from. Okay, and then I'm going to have my Geiger counter. And we're going to remember how this is set up. It's set up with this high voltage probe in the middle, and inside is full of argon gas, or an inert gas. And it's inert because we want only ionizations from this radiation to register. If you want to know more, there's a description of how a Geiger counter works we can look at later. Okay, so what are we looking at? We want to verify this idea that I is I naught over 4 pi r squared, where r is going to be the distance between the detector and the Geiger counter. So I can measure that distance, but you'll probably see here that there's actually, if the magic happens here in the Geiger counter, there's a little bit of extra distance which we haven't accounted for. We'll call that 1x. And so therefore we're going to get this systematic error to every measurement that we're taking between source and counter in the form of x. Now, we've said before as well that I know that the count rate is proportional to the intensity, so I can effectively say a small variation, the count rate is going to be the initial count rate divided by 4 pi r plus x all squared. Important because it's the total distance between the sensor and the source, so I've had to add those two together. Now this relationship here doesn't look the easiest one to plot in order to get the equation of a straight line, so let's do some rearrangement if we can. Let's move the r plus x squared up here, so I'm going to move that to there and that down to there, and that gives me c naught over c. Let's get rid of the square root, the square by square rooting, and then let me move the x onto the other side and slightly rearrange this as well. So I'll write it as root c naught 1 over root c minus x. In other words, y is mx plus c. So what I'm looking to achieve probably is if I plotted R against 1 over root C, I should get a graph that does something like that, where the intercept will be indicated by x. And of course the gradient here will be the C naught, but sorry, root C naught. But we're not too worried. Sorry. We're not really too worried about this. We're mostly interested in x to see how far inside that position, the Geiger counter, that sensor exists. This is an interesting proof to follow through. That's the first step, the first association to make. And then we work our way through the proof until we get to this point here and know what to plot against what. Now, it's probably fair to say that we do have these gammas moving out from here. Sometimes you might get other sources of radiation as well. There might be a beta or an alpha, but as long as that distance is large enough, then the beta and the alpha won't be able to cross through the air gap, nor this first part of the Geiger counter. So that shouldn't be a concern. However, there is a concern from background radiation that's going to be coming in from natural sources. So what we'll need to do is we will need to take that into account when we do our readings. So what will our table look like? Well, there's going to be lots of components to this table. We're obviously going to be measuring the distance r in meters. We're then going to be measuring the count rate. We are then going to want, and that's probably going to be something like counts per minute. We're probably going to do that once, twice, 3 times, and average it, because this is a random process. So therefore we're going to want to work out what's taking place as an average. We're then going to want to work out 1 over the square root of the count rate. And finally, hang about, small error there. We're probably going to want to work out, first of all, the corrected count rate. And then, finally, 1 over the square root of that corrected count rate. And once we have achieved that, then hopefully, once we've got the results in, we will be able to ascertain what this value for x is down here once you've plotted the graph. Good. Right, let's work out. So there will be questions where you have to do that and plot the graph. Fairly straightforward, I'm hoping. Let's try some problem sets now. Right, I've set up a question here that looks at the source of radiation, which is the same in both counts. At 2 meters from this source, the GM tube will have 0.36 microwatts per meter squared. So this is talking about an intensity that's falling. And when it's moved to another position, it gets 0.25 microwatts per meter squared of the GM tube. So we're going to work out what that distance x is. I mean, bearing in mind, of course, the GM tube doesn't detect intensity, and often these questions won't be set up with a GM tube and intensity to confuse. However, I think it's nicer to see a detector and work out that appreciation that intensity is directly proportional to the count rate. Okay, let's try and solve this problem then. We know that the intensity, which we measured, is I naught over 4 pi r squared. No n corrections issues to deal with this time round. So what I can do in the first instance is use this data to work out what I naught is. And then, knowing what I naught is, I can then plug that in to work this out. So let's try the brute force method first. We want I naught is equal to intensity by 4 pi r squared, giving me 0.36. I'll leave micro in there, by 2 squared. And that gives me 1.44 microwatts per what have you, per meter squared. Okay, so in the second part, this one here, using that data, I know what the intensity is. It's setting up the equation again. R squared, then I can say that R squared is going to be I naught over 4 pi I. So it gives me 1.44 micro divided by 4 pi by 0.25 micro. And then if I square root that, that should give me 2.4 meters. Good. Well, there might be another way in which I can do it, in which I can say to myself that I1, which equals I naught over 4 pi R1 squared, when I rearrange that and keep it in algebraically, I1 4 pi R1 squared is I naught, and therefore I divide that by 4 pi R2 squared to give me I2. And you can see all these bits drop out. So I'm simply left with I1 over I2, a little bit of quick rearrangement there, and bring this up. Or let's say, just for ease, I'll do that the other way around. So for I2 over I1, that gives me R1 squared over R2 squared. So that's a little bit of a neater way of solving the problem, if you can see how that works directly. Right, let's try another type of problem. Okay, now, this is dealing with that, it's dealing with a consequence of the unit of watts per meter squared. So let's imagine that we had a source, gamma radiation, and that I detect at a point, say 0.4 meters, 100 microwatts per square meter at that distance. Now that, okay, so that's telling me in effect what's happening over this entire sphere of 0.4 meters. How much intensity is falling per square meter? Detectors, on the other hand, are rarely that large. You probably have a detector area of, let's say, 5 centimeters squared. So in actual fact, what is the intensity that falls on that detector? That's the question that might be asked. In which case, it's a simple sum, but one we ought to mention anyway. We can say that the intensity multiplied by the area gives you the power that's fallen on the detector. In other words, if we have 100 micro multiplied by 5 centimeters squared, so that gives us 100 micro multiplied by 5 over 100 squared, converting it from centimeters squared into meters squared, which gives us 0.05 micro watts that have fallen totally. It's a subtle idea, but bear in mind that when you get that figure, it's for the entirety of this sphere, of which you have a small detector area, so GM tube, let's call it. Good. And finally, we're going to look at the penetration depth of gamma. This is probably a little extension to what we need to know. However, it's always good to appreciate that as gamma and other radioactive substances, but as gamma approaches a material, the intensity of that material, the intensity of the gamma ray initially will decrease as it goes through the material. Be a decrease in the intensity. In actual fact, the rate of absorption of the intensity with regards to the distance of material it's travelled through is going to be proportional to, of course, how much intensity you start with. If there's a lot more to start with, then there'll be a bigger decrease. This is the definition of exponentiality. And if I were to rewrite this slightly, whoops, wrong one. If I were to rewrite this, I would remove my constant of proportionality, and I would write it as minus a constant times the intensity. And you're probably aware that this looks very much like the exponential decay with the count rate, or even capacitor decay. So we'll just do exactly what we did with those. We rearrange it, di over I is minus mu dx, and then I'll integrate that between 0 to x, how much material it's gone through, and integrate this between an initial intensity and a final intensity. And then I won't bore you with the maths. However, it comes out with something like I is I naught e to the minus mu x. So this is the end product of that differential. Maybe I should have just put a minus there, because it's talking about how much decreases. If I were to draw a nice graph inside trying to show the intensity given with this distance, it will decrease from an initial point exponentially until it exits. So it might exit with some intensity remaining. It might not, depending. Last but not least, we can therefore infer from this value here, which is the absorption constant, absorption coefficient, which should be measured in per meter, an idea of the distance required to get half of the intensity, which of course is going to be ln2 divided by the absorption coefficient. So, in other words, how far do we have to go in order for the intensity to drop by a half? This is just like the half-life equation. Okay, that's a little bit of extension, but hopefully to give you an appreciation of how these things are absorbed through material.